Good afternoon, everyone. I'm Ekaterina. I'm a postdoc in ADI in the group of Alfred-Wegener-Institut. There's a little bit problems with plots, but I guess it's okay. Well, our project works with the internal wave generation in the Arctic Ocean, and my role, particularly in the project, relates to the tidal forcing component. I think it's worth to say that in the time scale of the project, we are in the beginning. So the main aim of this presentation is basically to introduce us to the community, to send the message that we are interested in collaboration, that we're interested to compare the results. So yeah, basically present our project. The research hypothesis of the project could be formulated following. So it's schematically in the picture, and also I will try to explain the algorithm that we are trying to investigate. So in the current ice declining phase, we get the reduced ice color in Arctics, and we anticipate that this phenomena will make stronger wind and tidal forcing, which in turn will generate more internal gravity waves. And enhancing internal gravity waves will lead to the stronger interior mixing and correspondingly weaker stratification, which for us is important. For us, important the entire water column, but particularly the weakened Kellogg line that separated the ice from the warm Antarctic water. So we are expecting that the heat flux from the warm Antarctic water will penetrate up towards the ice, and thus this even more increase the ice melting. So we end up in the positive loop. And this is the global hypothesis for the project to check. And as I mentioned, my course there to look at this from the perspective of the tidal forcing. So what do? We ran and analyze high-resolution global simulation with a particular focus to Arctic Ocean. We apply explicit tidal forcing to investigate the impact to many metrics, to the ocean stratification, to sea ice components, and overall we want to estimate internal ice generation. So what is adding particular flavor to the Arctic? That actually there we are living in two regimes where waves generated by tides could freely propagate, and they also could bottom out. Waves are freely propagating that then when they are limited, when the frequency of waves is limited between the periodic frequency and the buoyancy frequency. What is going on when we are going up? In the latitude, the periodic frequency increases, so at some point, that it has been mentioned already before, we reach some critical latitude. It's different for different tides. So basically for M2 tide, it's starts quite low, so almost all the Arctics below the critical latitude for the M2 tide. For the other tides, it's starting a little bit higher. But anyway, so we are living in Arctic in two regimes where waves are free propagating or bottom trapped, basically their movement following the topographical regime. So here I would like to mention that we are running the global ocean model FESOM, and we run 4 global simulations with the emphasis on the Arctic Ocean. That means that around 80% of the mesh nodes located north from 60 degrees. So basically, most of it focus on the Arctic, and we have rather coarse mesh in the tropics, in the south, etc., which is not a focus of our research. We did already the spin-up of the model, so 35 years, and we took the last year as the reference here. Here on the plot, maybe it's, I want to point your attention to the green line. It's temperature dynamics around the level of Kellogg line, so it's around like 150 meters depth. And if the first 20 years it was still increasing, so after like last 20 years it's reached plateau, and we think that it's acceptable level to spin up for our research, so that our results will not be biased or significantly biased by still temperature modulation and temperature settlement. And we set 4 simulations, so with tides and without tides, with levitating ice and with embedded ice. Here, I introduced terminology, embedded ice and levitating ice. It's actually, I would refer here to the paper of public shorts from 2024. So we realized that in the global ocean FESOM, you actually can choose what is the configuration of ice you are using. And standard in the modeling community, or it seems like it's a standard because it's actually a little bit flexible and faster and simpler. It's levitating ice when ice in the model does not actually share the grid with the ocean, but sitting on the top of the ocean. So it's called levitating, so actually there is a clear boundary, and the ocean grid starts below the ice. And for that kind of simulation, the model doesn't require specific conditions or works with, the model can work with different vertical coordinates, so there is really few limitations to run the model. But we found out that significantly less popular, but for us very interesting, and we think that physically motivated ice configurations, embedded ice, when ice is sitting on the top of the ocean, so it shares the same grid with the ocean, and it actually has the particular component to the pressure calculation in the model, so it actually has additional component to when you sum up all pressure, when you sum up atmospheric pressure, hydrostatic pressure, and you also get pressure from the ice. And maybe to convince you even more, or convince even us that it's different. So we check the sea ice concentration difference between these two setups just for 1 month. And it's indeed, so it's basically sea ice concentration difference, and it's indeed exists. It kind of generates somewhere in the topographic slopes and it's propagated further to the ocean. And it's actually aligned with the work of Patrick, who found that embedded ice configuration is more prominent in some complex topographic structures. So it's better capturing the reality, or whatever, better aligning observations. So therefore, we run in parallel simulation with tides, without tides, and with 2 different ice configurations. Well, let's go now to the output data of the models that we run. So first, on the left, I just want to show you how on that grid sea ice concentration looks during the time span of 1 year. So we reach the maximum ice extension on March. We reach the minimum ice extension on April, or on September. Yes, so and this March and September we have chosen particularly for our tide analysis. So because to produce tide data, we need really frequent output. Not less than hourly, and with the global ocean model, we cannot afford like years of hourly simulation. So we particularly concentrated on March and on September, analyzing our tides. Also, it seems like it's convenient and interesting to use the sector analysis in the Arctic to consider the effect on ice within the sectors, because there is a difference. So we want to be aligned with other authors who did the similar studies or the similar direction of the studies, and we also do the sector analysis. And here I put the sectors that we are using for Arctics. Since we run our model with tides, the first thing that we want to see actually how good are these tides in the model. So before, since we activated the tide regime, the first thing that we wanted to see if we are capturing the amplitudinal points in the global ocean world. What are the amplitudinal points? Is points in the ocean where essentially the amplitude of tides almost or equal to 0. So you can see on the top plot, it's a dark blue spots in the map where the effect of tides is minimum. And also below, we see the phases around these amplidromic points, basically how tide overturning these amplidromic points. And we did the validation of our model output data in the Arctic versus the observational data. And here is a scatter plot how amplitudes of some points, amplidromic and also non-amplidromic, is captured, and how the phase is captured. So the more it's aligned with the 45 degrees line, the better we are fitting with observation. So what we see here that in amplitude we are pretty much good, especially if we are talking about like surroundings of amplidromic points around zero, where amplitude is around zero. With phases a little bit more tricky, but this is the results that we anticipate, because in that kind of resolution, we capture not only amplitudes but also phases. It's quite a task. So, quite a task. And what's for us important that, for example, some main or important amplidromic points and phases we are capturing, for example, the one that lay under Greenland, maybe you've seen the dark spot under the Greenland, and basically aligned with the entrance to the Arctic from the Atlantic Ocean. We correctly get the phase, so the rotation of tides anti-clockwise, so that's what we expected. What is aligning with the Coriolis in the North Hemisphere. And we also check some like important points for us, so and they highlight. So with that validation procedure, we are satisfied. Then we had a look to within our core simulations to the pressure transit. So you see it here. It has been chosen in the most fluctuable area in the Atlantic sector. And we took the, well, rather small but very popular in oceanography transect around the Svalbard in that you can see. And we checked the pressure output from 4 different simulations. And here you can see the bar is aligned between 4 of them, and it's very different. So we do see a lot of results depending if we have tides or don't have, and also which configuration of the ice we have taken. So this is kind of interesting and complicated, because interesting, so whatever we will analyze in the future probably will give us quite different results. But complicated because overall we need to give an answer to our research hypothesis, and since configurations are so different, might give different results, so we might be trapped with this variety, but we will see. It's still ongoing research. Of course, we also did the spectrum. We had a look how nice, so that's the spectrum for big ramp. Sorry, I'm a little bit Russian. So there are long-term talks and debates in the publications about the decomposition of pressure into surface and internal tides. Here we probably are not jumping yet to the data, so we started with the basic or with the most simple decomposition, where we separate instantaneous pressure into the depth average and the residual pressure, which is like pressure, total pressure minus depth average, and our residual pressure is actually internal tide pressure. And for this P prime, we plot the spectrum. We observe that we are capturing pretty much well peaks for the semi-diurnal M2 peak, for the diurnal tides also peak. And here, so when you think about the ice concentration expand or ice concentration decrease, the first intuitive idea that comes to your mind is like to see the heat flux that going up or down to the surface. And that's what we checked. We checked the ice concentration in particular region. It's again Antarctic sector. And also we had a look to the heat flux. And we wanted to see how simulation with tides and without tides influence on these two indicators. Well, as I mentioned, we took March and September. So what you can see here, that simulations with tides, here it's a dashed lines, they have high ice concentration in March and lower ice concentration in September. And also, if you we'll have a look to the slopes, how within the time the ice concentration is changing, is pretty different. So, for example, in September, tide simulation already start accumulate ice. Simulation without tides are still declining. So that brings us to the ideas of how complex introduction of tides even within one region and even like within 1 year. So definitely seasonality will matter, and definitely the choice of the ice will also matter, because here if you will compare the orange versus blue, then the slope is pretty much different, and it's just for one region. So we are digging deeper to different regions. And for example, if you will see the small transect in the Translate, the pictures will be absolutely different. So we are kind of in the stage when we are trying to find some trade-off or balance. If we look to the entire Arctic, picture looks pretty much similar. If we take some transect, picture looks very different. So we are somewhere to analyze our data in some intermediate geography, let's say, intermediate domain. And if we look to the heat flux, here picture is even more controversial. So all this sinusoidal curve, it's tidal heat fluxes. So maybe I should say. So left column is March, right column is September. Top row is surface heat flux. And here we just jump a little bit down to the 20 meters to see if picture starts changing within the depth. So, and indeed, so you remember that ice concentration was sloping from the March and September between tides and no tides. The heat flux did not do this, but for example, in September, heat flux with tides sloped with the depth. So we went a little bit go by that, and the orange and blue line changed the position from each other. So with all this, it might look a little bit complicated, but it is. So the thing is that even with that analysis, we came up that if we want to make this path from the tidal forcing to the sea ice concentration, and if this path will go through the heat flux, we will meet a lot of points rather complicated to interpret. So we already found that seasonality matters. Sorry, maybe I repeat this. That seasonality matter, that choice of ice model matter, and also like the depth where we analyze the heat flux also matter. So with that, with this kind of ideas or hints, we will go rather to more high resolution simulation, and we will continue analysis. So all this has been done in 4.5 kilometer. So now we'll go further, and we will again double check all these results and try to tell the story, how that goes. And here also one interesting metric that we found so far, bottom buoyancy frequencies. So we took the belt of the bottom of 250 meters in the entire Arctic Ocean, and we plot the n square, so bottom buoyancy frequency for the simulation with tides and without tides. This n square is basically the parameter that shows us the stratification. The higher n square, the more stratified the flow. So we want to check the stratification of the bottom of the ocean. And on the very right plot, since first two, it's hard to differentiate by ice, like what's going on. So I took the difference to highlight where are the epicenters of the difference. And what we see, so indeed, if we consider the entire Arctic Ocean, tidal forcing has a very heterogeneous impact on the bottom stratification across the entire Arctic. We see that in the Atlantic sector, so the entrance between Greenland and North Europe, tidal and non-tidal simulations show minimum difference, indicating that stratification primarily controlled by strong inflow from the Atlantic and by mixing process rather than by tides. At the same time, that might be not a surprise, but it's nice to see it on the plot that all the Siberian shelf area, all the area of the freshwater heat flux where the data of river is very, very much different with tides and without tides. And we tend to see that it's, so although there are alternating patterns, it's blue, red, blue, red, it's a little bit tend to be more blue. That means that tides tend to enhance bottom stratification. So for tides, we have higher n square. And yes, that's it, and that's a conclusive slide. It's actually not a conclusion about the plots, it's more like the roadmap where we go in further. So our final aim of the project to make the IDEMIX, the internal wave model, as a primary parameterization in FESOM for the internal gravity wave mixing. And we want to adapt that to the Arctic region. So the model should be fitted correctly by tidal and by wind forces. So for now, I'm trying to dig deeper into the tidal forcing to make it more realistic. There's another person who is digging deeper into the wind forcing, and we are expecting that with our cumulative work, we can adapt it correctly to the Arctic. And well, maybe it's too early to talk about the future, so probably let's talk about that. We want to do it for the climate, for the current climate conditions, to work it well. But if we succeed, we will take a step to the future climate conditions. So yeah, that's it. If you have any questions, or especially comments, or especially corrections, that would be really cool.